Greetings and welcome once again to my new calculus channel. My name is John Gabriel. So in the previous video where I'm discussing what is time in part 2, I stopped just before the topic of what is a unit of time. So now, you know, we think of a unit, but where does the concept of unit come from? Again, it comes from a ratio. Okay, so it comes from deriving number the correct way, not from the garbage of set theory or von Neumann ordinals or all that BS. That's just total nonsense. Okay, you can't derive it properly, and I've also provided uh, resources for you to study on that. So I have an interesting article asking, can you derive numbers from set theory? And I explain why you can't. So I'll probably place a link to that as well. Also, I'll place a link to this excellent article on exactly what is a rate. Okay, it's very important because I start right from the beginning and I show you how you arrive at the concept of number, how you arrive at the concept of a unit. And why would you need a unit? Because you want to be able to measure things, quantities, and fractions of numbers and rates and all those things. You need a unit. Okay, it's and not just a unit. It's an abstract unit because when you talk about numbers, they're all defined in terms of the abstract unit. Even in algebra, uh, everything that you have is represented using the abstract unit. And of course, you can add a physical dimension like a length or a mass unit or something like that, but you don't have to. For example, when you're calculating an area under a curve, um, you're taking the product of two level magnitudes or arithmetic means, but neither of those have dimension. It's just the level magnitude of the y ordinates multiplied by the level magnitude of the x ordinates, which is also known in the mainstream incorrectly as arithmetic mean. But so what is a unit? And that is what we're going to discuss now in this video. And look, I'm sorry that I'm not able to prepare these videos in advance, but I reckon that if I had to do that, I'd never produce any videos. So all my videos are impromptu. So now, as we saw in the previous video, we need both matter and almost constant repeatable motion for time to exist as a well-defined concept. Otherwise, time doesn't exist, okay? And we know that the Earth's rotation speed is approximately 463 meters per second at the equator. Therefore, what that means is that 463 meters are covered in 1 second. And that's our clue as to how we define unit. How do we define unit? Like this. How do we define second? 1 second is just simply 463 meters divided by 463 meters. Okay, it's as simple as that. So now you have a time unit, which is a second. All right. So, and that means that if you have another object that travels at the same speed as the Earth at the equator, then a distance of m meters takes m over 463. And why is that so? Well, guess what? It's just simple proportion. Okay. So if 463 meters gives you 1 second, right? Meters, then m meters will give you by proportion m divided by 463 times 1. We don't have to bother with this times 1 part. It's just m divided by 463, and the result of this will be seconds. Okay, so let's clear this board quickly so that if we need it, we have it. Okay, so to measure time with respect to different speeds, 1 second represents 463 meters at a speed of 463 meters per second. So if an object, for example, travels 100 meters at the same speed as the Earth at the equator, then the time taken is 100 divided by 463, which is equal to approximately zero point 0.2 seconds. Okay, so again, how do we do that? That's simply proportion, isn't it? Okay, because as I showed you here, so if you have 1 second gives you 463 and you have 100 and you want to find seconds, it's just 100 divided by that, right? 100 divided by 463 times 1. Don't have to bother with that, okay? So that's what the article is telling you. Now, if an object is traveling at x meters for 3 seconds, then how much distance has been covered at the Earth's equator from an object's fixed location to its new location? And the answer is pretty easy, isn't it? It's just simply 3 times 463.8, isn't it? We don't even care about this because all we need to worry about is the fact that 1 second is equal to 463 meters. So notice that the speed x m by m over s of the object has no effect on the calculation. All right. So I'm telling you that a lot of physicists don't even know this. They're totally clueless. They're brainless. Okay, so when we think about a second, we're really thinking about the standard time unit, which tells us that the time duration takes as long as the Earth does to cover that distance of 463 meters at its equator. Okay, and another way to think of this is to think of the distance 463 meters being traversed at the equatorial rotation speed of the Earth. So everything, by the way, everything, water clocks, hourglasses, atomic clocks, etc., are all calibrated to the Earth second. I mean, what sense would it make to calibrate uh, time according to the rotation of any other heavenly body? Because we have no familiarity with it. We have no familiarity with how long Jupiter takes to rotate or the moon takes. Well, moon we do more familiarity than Jupiter, but with the Earth we have a very strong connection and a very strong familiarity. Why is that so? Because we know approximately when a day starts and when a day ends. Sunrise to sunset. Makes me think of that song. Sunrise, sunset, sunrise, sunset. Okay, never mind. Let's not go on a tangent. Now, so if an object travels 650 meters in 1 second, then we know it takes as long as the Earth takes to rotate through 463 meters. Okay? That's what it means, by the way. Let's think about, stop and concentrate on what I'm telling you. So if an object travels 650 meters in 1 second, then we know it takes as long. Okay? The clue is as long as the Earth takes to rotate through 463 meters. So what does this just basically tell us? It means that uh, everything that we do is calibrated to Earth time, and especially at the equator. So let's think of this as the equator here, right? So if you have a point here, let's say a big point here, and 463 meters like this, is this distance here, okay, is this distance here, then we know that for the Earth to move from this so that this point overlaps this point, it's exactly 1 second. That's what it means. And that's how we recognize a second. So if we say 1,000, okay, then we know that's approximately a second. Okay? So these time measuring devices help us to understand a period of time by relating the time measure to the standard. And what's the standard? 463 meters. That's covered at the equator. Now, we have a good notion of the time, as I just mentioned, because we know approximately or more or less how much each day takes. In other words, what each day corresponds to in terms of the rotation of the Earth, right? So approximately one rotation is a day, which is 24 hours, and then multiply that by 60 to get the number of seconds. So, as I said earlier, it doesn't make sense to define or calibrate our time units to any other planet. Now, you'll notice once again, that mainstream knowledge sources will say that atomic clocks are not dependent on the Earth at all. They are dependent on the Earth. They're calibrated according to Earth time. So if you talk about so many cesium cycles, that's the case because That's approximately the time the Earth takes to move through 463 meters. So, time, by the way, is a very well defined concept. It has nothing to do with the nonsense of Einstein, Hawking, or any other theatrical, intentionally said that way, physicist. That is space time, time dilation, time expansion, curvature of space and time, arrow of time. So, I'm going to discuss can time be dilated or contracted? And uh, I'm going to explain the anomalies that Einstein noticed. And by the way, it's not going to be in this video, in a future video. But none of those things have anything to do with Einstein's bogus ideas, okay? So I address all the experiments, the Eddington experiment, the Heathfield-Keating experiment, and I show you why you can't think of these things the way Einstein thought of them, because they just don't make sense the way he thinks it. He didn't understand them. So, and somehow all the so-called every Tom, Dick, and moron who came after him somehow understands, and they consider him to be a genius. So, in other words, they're saying they're even smarter than the genius. Okay, never mind. So, one thing I want to end off is that it's got nothing to do with time dilation, space time, expansion, curvature of space, or the ultimate bullshit called the arrow of time, etc. Don't go to Wikipedia, please. Whatever you do, don't read up anything on Wikipedia. It's all garbage. If you look at Wikipedia, you do it simply just for reference, but you cannot trust the information on Wikipedia, and you have to think about everything you read on the internet. Okay? So the next thing we're going to do is discuss clocks, but before we do that, we need to define time. So, as I said, time is the name given to a distance that describes the motion of a certain body or matter from one position to another at an almost constant motion. Okay, it's very important that the motion of the body is almost constant. So, if one is using radioactive decay, then the distance can be replaced by decaying mass, in which case you wouldn't be asking how long, you would be asking how heavy or how light. How light is it or how heavy is it? Okay, it's got nothing to do with distance in this case anymore. But mass is a far more complex concept than distance. Distance is relatively simple and can be systematically derived from nothing, from a void universe, so to speak. So another definition for time could be it's a name given to a mass that describes the metamorphosis of a certain radioactive material from one state to another in an almost constant way. That is, it loses the same amount of material from one state to another. Now, this may appear circular, but it's not, because the amount of matter lost must be almost equal after each change in state. So, regardless of which definition is used, both the scalar and the motion metamorphosis must be calibrated in a device so as to emulate Earth motion, Earth movement, almost constant Earth motion. In other words, Earth time. All right? In other words, distance covered by the repeatable constant motion of the Earth. Now, excuse me, coordinate universal time is the basis for civil time today, and this 24-hour time standard is kept using highly precise atomic clocks combined with the Earth's rotation. Okay, note that the atomic clocks are used for UTC and they are calibrated using the Earth's rotation as standard. Just imagine telling someone, I'll arrive once this lump of cesium decays to 0.98 of its current mass. Chances are that person will never arrive on time. Why? Because they have no familiarity with that. If you say arrive the next day, a person might arrive on time because they have familiarity with that time. So it makes no sense to define time in any other way but as it relates to Earth time, because we live on Earth, right? So Earth time was chosen because we can relate to it in a very meaningful way. Can you imagine telling somebody to measure seconds in cesium cycles? It's absurd. Okay, this is obviously unworkable. Now, when do we do that? We do that when we want to get slightly more precise measure, but it's not accurate, because accurate means it's 100% correct, and there's no such thing as accurate time measure. So, uh, so Earth time is the motion of the Earth when it moves approximately 460 meters from one position to another, and it's called 1 second. All right. Now, I'm going to stop here because in the next episode, I'm going to discuss Einstein's ideas about GPSs and time anomalies and what have you. If you're not already a subscriber, become one. Follow me on academia.edu. Tell your friends about this channel. Click like. And uh, hopefully, I'll be in touch with you pretty soon. My name is John Gabriel, and this is the New Calculus channel. Till next time, goodbye.